research here at University of Arizona. Oh, thanks for recording this. And I do a bit of work with forecasting tree ring and forecasting forest growth responses to climate change. And that work has led me to need to use Bayesian statistics and Bayesian analyses in R. And so my goal today is to sort of share some of those resources with you. And before I jump into objectives, do you want to introduce yourself, Jessica?
Hey everyone, my name is Jessica Guo. I'm a scientific programmer here in the College of Agriculture and Life Sciences. I'm also a Bayesian ecologist by training, and I'm here in the helper role. But especially if you have questions about some of the scripts or the binder, that would be me. And you can also, I will be monitoring the chat while Kelly is presenting her materials.
Perfect, thanks. Yeah, so last year I did this tutorial and there were a lot of issues with making sure everybody had the right software on their computer, and downloading JAGS can be kind of a pain. And so this binder instance I think is going to be really helpful. So thank you for that, Jessica. So I'm going to do a brief overview of the HackMD, the GitHub repository, and the launch binder before we jump into objectives. So I have here sort of the steps. I'm going to stop sharing that and go to the HackMD. So here it looks like most people have been able to add their introductions, which is great. We also have the same link to the GitHub repository, as well as some alternative instructions if you want to, say, download and install JAGS itself and use this on your own computer. And then if you have any sort of like lingering questions during or after the workshop that you aren't feeling are getting answered, you can ask them here. I would say we'll probably see it quickly in the chat. So that either one of these is a good way to ask questions. And then at the end, please fill out the session feedback form. That'll be really useful for us. Okay, so let's go to the tutorial, and I'll give you an overview of that. So it's on my GitHub. And so you can see the repository here. We have a README, and then this is the launch binder button that you'll click to access the workshop. I have already clicked it and opened it, but yeah, feel free to do that. It'll take a little bit of time to load. So has everybody made it this far? Can I get thumbs up, thumbs down? Okay, got a couple of thumbs up. Is there anyone that wants us to wait? Let's see, waiting on, okay. That's fine, that'll take a little bit while people are waiting for the binder to launch. I'm gonna go through what it should look like when it launches. And start going through, there's like a PDF where we'll go through some basics before we start doing any sort of coding. Okay, so when it launches, it should look something like this. And I'm going to give you an overview of, let me get my, there we go. Okay. So you'll notice there's a bunch of files in the home directory. If you're familiar with RStudio, this will look quite familiar. You'll notice that there's a PDF, and so this PDF is basically the whole workflow that we're going to try and get through today, along with some introduction to Bayesian statistics, as well as a couple of different examples, running a Bayesian linear regression, as well as a regression with random effects. And And so we can click on that and it'll bring up this PDF, which we'll start walking through. And then at certain points, I'll ask you to open different R scripts. But while we're waiting for this binder to launch, we can go over some of the overview here. I don't think the PDF got
this is a previous version. I don't know how much that matters. You did add some materials.
Good point. I will share another window then. Okay. Up here, let me stop share. Here we go. Okay. So this version will be slightly different than what's on the binder instance, but I will push this up to GitHub at the end of the repository, or at the end of the workshop. That way, if you guys want the most updated version, you can go back and look at it. Okay, so what we're going to do in this workshop is cover the basics of Bayesian statistics, go over an example of how to specify a linear regression in R using JAGS. And here again are the prerequisites. Launch the virtual RStudio by clicking the launch binder button in the README file. And so my goal here is to cover the very, very basics of starting to use Bayesian statistics. Oh yeah, thanks, Jessica. And to go over an example of how to specify a linear regression in R. And at the end of the tutorial, my hope is that you're going to have a better understanding of Bayes' theorem, as well as get some experience running a Bayesian model in R and JAGS, which, as Jessica pointed out, is called just another Gibbs sampler, which is a way of doing MCMC sampling in R. And we'll talk a little bit more about that later. And then at the end, we have a bunch of like further resources, as well as some things to watch out for. Okay, so why should you think about using Bayesian statistics, or what are the advantages of this? So the first is that all parameters are actually treated as random variables, and this can include our data. And so this is like, rather than assuming that our data and covariates in our models are single true estimates of that process, we're acknowledging that the values are actually coming from a distribution that represents the true value of the process that we're interested in. So for example, in my field, I measure the size of trees. So the diameter of a tree is an important quantity for a forester. And so I might go out in the field and measure it with my diameter tape. But I know that that's not the true diameter. I know that if somebody else went out and measured it, it'd be slightly different. I know that at different times of the day, the tree has a different amount of water. And so there's variability around the measurements that we take. And so Bayesian statistics allows us to explicitly account for this variability and include that uncertainty in our models. And speaking of, Bayesian statistics often allow for estimation and parsing different sources of uncertainty. And so the estimates that we get from our Bayesian models of parameters or of predicted values that we're interested in can actually include things like process error, uncertainty in parameters, so uncertainty in like the effect of a particular process on the data, data uncertainty, as well as things like driver uncertainty. And so this I often think of as, you know, if we're forecasting into the future, what's the uncertainty in future climate drivers? Or what's the uncertainty in future like human decisions? And then the third advantage that I think is important is that Bayesian methods can really accommodate hierarchical and different process models. So it can do things like borrow strength across different groups or treatments. This can be helpful if you have a lot of data in one group, whereas very little data in the other group, but you know that they are somewhat linked or hierarchically structured. You can borrow strength in that way. You can also specify like more complicated or appropriate distributions, different process models, things like state space modeling, logistic functions, etc.
Interject here for a moment,
Yeah.
Kelly, before you move on. One thing that I was super excited about to become a Bayesian from a, start off as frequentist is that the first bullet point here means that you don't need your data to approximate a normal distribution in order to perform the ANOVA, the t-test, the linear regression, because it knows that the distribution of tree diameters, for example, is normally distributed, but you may not have, your 30 trees that you measured may not approximate that. And then, so if you were doing frequentist, this is where I would twist myself in knots trying to transform the data, make it normally distributed, make it, check for heteroscedasticity. Man, I hope I'm saying that right. And then it doesn't, it's not very interpretable. Like once you have I had negative, I was doing something that the values were negative, then I had to transform them to be positive, then take a log, then it was normal, but then none of the parameters made a lot of sense because what does that even mean? Nobody knows. So that from a very practical and frustration driven point of view was a super advantage of Bayesian analysis when I was starting off. And maybe you'll find that too.
Yeah, that's a really good point. You can actually model the data using unscaled or at the scale that the data is actually at.
Or the appropriate distribution. You can count data, you can approximate it as Poisson or something and not necessarily as a normal.
Yeah. Okay, so I guess to get a feel for where everyone's at, in the chat, do folks want to add are you familiar with Bayesian methods? Are you a newbie? It'd be great to get some feedback on where everyone's at here. Novice, newbie. Okay. So some practical experiences, calculating, oh boy, Bayesian factors, but that's pretty much it. Moderate user, attended a week-long boot camp, great. Generally familiar with concepts, somewhat familiar. Have been teaching myself, but don't know how to interpret. Yeah. Okay, so a couple of people have said you've had some exposure, don't understand it enough to teach it, not confident to do a full analysis on my own. I've been there. Some aspects of Bayesian, I'm still there. But yeah, I guess one thing I would say, maybe Jessica and anyone else can chime in, I was exposed to Bayesian statistics a couple different times throughout grad school. And each time I took, different aspects of it, but it took me a few classes, workshops, just working through it on my own to really start to be able to implement a model on my own. So hopefully you can all gain something out of this. And I would say, don't give up. It'll click.
The other thing is that Kelly and I are trying to start a Bayesian reading group on campus. Oh, of course, it's virtual also, so you don't have to be on campus to join us. But and during the pandemic, it's hard to find the people you don't already know who are also Bayesians. So not just our lab mates. So part of this at the end, we'll ask for maybe some of you to write your emails in or note on the HackMD whether you're interested in this reading group or not. And so try to get together and help each other out and maybe just talk about our problems Bayesian and see if the group can collectively come up with some way forward around those blockers. I'm envisioning low commitment every other week, an hour. Like, I know everyone's busy, but hopefully we'll build a community of practice.
Yeah, I'm excited for that. Okay, so we will go over Bayes' theorem while trying not to give away my answers. So many of you may have seen something like this before, but so Bayes' theorem is basically the basis for Bayesian analyses. And what it does is it states that the conditional probability of A given B, so that's what this notation is saying, the conditional probability of A given B is equal to the probability of B given A. So this is the likelihood function here, multiplied by the probability of A and normalized by the probability of B. And so this probability of B given A is the likelihood function. Probability of A is here, it's the prior or the marginal probability of A, is what you might be familiar with. And then B is the marginal probability of B. And there are different ways of presenting this, like often when we're talking about a model, these A and B's get transferred into the model and the data. Jessica, do you want to add anything to that?
No, it's just, I feel like the theory part is really interesting, and the probability, it's like definitely the foundation. But from seeing some of your comments, yeah, so the newbies, yes, this is the theorem. For the people who are trying to figure out how to use it, it doesn't actually come up that much. It's just like, it doesn't come up that much when you're trying to actually specify a model, get it to run and converge. So
yes,
the applied versus the theoretical, I guess.
Yeah, we will use this concept of a prior and a likelihood, but transferring the Bayes theorem into a working functional model, there's like a big jump there. At least for me, there was. Okay, so let's review a little bit. So we can review probability using a Venn diagram, and I'm actually going to jump out of this PDF really quick into let's see. Okay, so let's use Bayes' theorem. Share my screen again. Okay. So let's use Bayes' theorem to calculate the probability of A, the probability of B, the joint probability of being in A and B. I guess, well, okay, so let's start with the marginal probability of being in group A based on this Venn diagram. So pink here, all the dots are in group A, blue, the dots located in that circle are in group B, and then the center here are dots located in A and B. So in the chat, could you put in your marginal probability of being in group A? So one thing to do is count up the number of dots. Okay, so we've got 5 out of 12 are some of the guesses. So we've got 1, 2, 3, 4, 5 dots in group A. And then we have 1, 2, 3, 4, 5, 6, 7, which would make 12 dots. So, oh no, where did it go? I don't know how that happened, but Okay. So we have 5 out of 12. Great. So similarly, what's the probability of being in group B? In the chat. Let's see. All right, 7 out of 12. 9 out of 12. We've got 1 9 out of 12. Okay, so Luke, do you want to say why it's 9 out of 12 instead of 7? Either in the chat or unmuting yourself. Yeah, you're right. So when you're, so you got to count up all the dots that are located in group B, regardless if they're also in group A. So that'd be 9 dots here. Okay, how about the joint probability of being in A and B? So we've got, 2 out of 12, which ends up being 1 out of 6. Okay, cool. And then using Bayes' theorem, what's the conditional probability that we're in A given that we're in B? So I put Bayes' theorem up here. All right, we got a couple, and Luke and Melton, you're right, 2 out of 9. So could you type in how you got to there? Yeah, so the conditional, then count the dots in the union. Okay, so count the dots in Venn diagram B, which is 9, and then count the dots in the union, which is 2. Okay, so then what's the conditional probability that we're in B given that we're in A? All right, cool. Anthony got it. 2 out of 5. Luke got it. So I do this, like for some people, this is like, seems very basic, but it really, probability never clicked for me until I saw it visually. And so this is sort of like trying to introduce the material in a couple different ways. Okay.
Before you leave this, Kelly, could I actually say something about, I agree that the visualization is key. So you guys might have seen like the Bayes theorem written out for Bayesian modeling as key of parameters given data. So like A being the parameter of interest, like the growth rate of trees, and B being the data, which is the bunch of tree diameters that Kelly went out and measured with her tape. So you can imagine this as being the red circle, the A is all the possible growth rates of trees out there in the world. And that's the distribution. There's this, maybe it's normally distributed. We assume that like there's this distribution of possible tree growth rates, right? There's real tree growth rates, but there's this whole spectrum of them. But for the trees that Kelly specifically went out to measure, once she went out and got the data, so the B, the dots in the blue circle, that limits the number of possibilities of that tree growth rates, right? Once she has the actual trees, say she's limited herself to ponderosa pines in Arizona. How did I know to pick that? For those trees, then the probability of that certain parameter growth rate is no longer everything possible, but like pretty narrow. And that's what we're interested in, right? That's what we want to report. We want to say that that's different from 0. We want to say that, tree growth rate is linked with temperature or moisture or CO2 or something like that. And so that's where that's where we're going with this. So we're not sticking with just the Venn diagrams and probability problems from like a math class.
Yeah, exactly. And I'm actually gonna okay, go back to this tutorial, which actually has that version of Bayes' theorem, where we have the probability of the model parameters, theta, or the model given the data, which we're calling x here, is equal to the probability of the data given the model, which is like your typical maximum likelihood frequentist version of likelihood. So you might be familiar with that. Multiplied by the probability of theta for the model, and then normalized by the probability of the data. Yeah, so this probability of the data given the model is the likelihood. I don't have my little pointer up. Back. Okay, there we go. Okay. Yeah, so this is the likelihood, and this probability of the model parameters or the model is the prior probability. So we'll talk a bit about the priors and the likelihood. And basically, yeah, I don't know how much I really want to talk about this, but the marginal probability of the data is the probability of x. And so because of this, we can use the integral of the joint probability x and the model over all possible states of the model parameters and rewrite this as this version. And basically, this is normalizing the function. We won't need to talk about that too much in order to actually implement this version of the model. But you might see this version of it in some other Bayesian textbooks. Okay, so let's go through another fun example. And this is like my favorite example because it uses an XKCD comic. I'm trying to get it all on there. And so this is an example from the Ecological Forecasting book, which is by Mike Dietz. I highly recommend it if you're interested in forecasting, but it's inspired by an XKCD comic. So it's about whether or not the sun just exploded. It's night, so we're not sure. And so we have this neutrino detector that measures whether the sun has gone nova. Then it rolls 2 dice. If they both come up as 6, it lies to us. Otherwise, it tells us the truth. So let's try. Detector, has the sun gone nova? So it rolls its dice. It says yes. So the frequentist statistician says the probability that the result is happening by chance is 1/36, which is equal to 0.027. But since p is less than 0.05, I conclude that the sun has exploded. And a Bayesian statistician says, bet you $50 it hasn't. So let's find out why the Bayesian statistician doesn't think the sun has exploded. Okay, so the neutrino detector tells us whether or not the sun has exploded, but it has a 1 in 36 chance of lying to us. So that's the chance that it'll roll 2 dice and they both come up 6. And so our data says, yes, the sun has gone nova. So we have 2 hypotheses if x is yes, theta 1 and theta 2. So theta 1 is that the sun is nova, theta 2 is that it's no nova. And so we'll derive 2 likelihoods, the probability that that the data says that the sun has gone nova and it's actually 1/36. gone nova. So it's a probability that a yes from the detector is not a lie. And then the second probability is the probability that the data says yes, but it's not actually nova. And that's the probability that a yes from the detector is actually a lie. So we can use Bayes' theorem to estimate the probability of the sun exploding, given our neutrino detector telling us, yes, the sun has gone nova. So that's the probability that the sun has actually gone nova, given that we have data that says yes from the detector. That's equal to the probability that we get a yes from the detector and the sun has actually gone nova times the prior probability that the sun has gone nova. And then in the denominator, we have the probability that we get a yes and the sun has gone nova, again, times the prior probability that the sun has gone nova, plus the probability that we get a yes and it's not actually gone nova, multiplied by the probability that the sun has not gone nova. So that was a lot of me bumbling through that equation. But we, this is in the R Markdown code that's on the workshop tutorial, so you can play around with this if you want. But what's really important here is that we can assume that let's assume that the prior probability that the sun is actually going to go nova is really low. So 1 out of 10,000 chance, which I think is still a pretty high chance, but we'll say it's pretty low. And we can put in our theta likelihoods in this R code, 35 over 36 versus 1 over 36. And then here you can play around with the prior. Here, let me actually, yeah, I guess I'll just stay on this. And then the prior for theta 2 is just 1 minus the prior for theta 1. And then we calculate our posterior here, and I'm having the code print the probability that the sun just went nova. And so there's a 0.03499% chance that the sun actually just went nova. And so if you play around with a prior belief, say if you make this 1 out of 100 or 1 out of 1,000, you start to get a much higher chance that the sun actually just exploded. And so what I'm trying to illustrate here is that the prior belief can be incorporated into your models or into the analysis of whether or not the sun actually just exploded. And so here we have a pretty informative prior belief that the sun has not actually exploded. But if we have a strong prior belief that the sun did explode, that would change the little cartoon guy's response here. Yeah, so I like to walk through that example just because it's fun, and XKCD comics are great. Okay. And I'm going to actually show you a bit where that is. Okay, so if you're on the HackMD, this R Markdown won't knit for you. But it should, like, you could still run this aspect of the code or copy and paste it. So we'll run these and we're getting a really small chance. So let's make this 1 over 100, and we can see how much that changes like if we change the prior to being a stronger prior belief that there is a larger chance that the sun actually exploded, we end up getting a 26% chance that the sun exploded versus what it was before. Okay. So to see where everyone's at, has everyone been able to get the binder launched? Okay. Seeing a lot of thumbs up. Took a long time. Yeah, it does take a while. So if you haven't already tried to launch the binder, let us know and we can talk you through that again.
This is probably also an appropriate time to open up JAGS_regression.r. Follow along Kelly in this next section.
Yeah. So that is this guy.
So this is the same thing that's in the R Markdown, but it's just a single script. So it's all the different chunks in one place, and you can run by line as you need it.
Yeah. Okay. So we will, let's see, I'm going to go over one other background. Binders up. Cool. I guess another background example of how we can start to use Bayes' theorem to estimate model parameters. So let's say we have a normal likelihood that has a mean we'll call mu, a standard deviation we'll call sigma, and we observe a value of our data x is equal to 15. And so let's estimate and use Bayes' theorem to determine the posterior probability of our parameter of interest mu given our data at x equals 15. Okay. Hopefully that, see that a bit better. Okay. Get my pointer here back up. Okay. And so the posterior probability of mu given the data x equals 15 is proportional to the likelihood multiplied by the prior probability of mu. So that's what this is this equation is referring to. So the probability of mu given the data is proportional to the probability of the data given mu, our likelihood, times the prior probability of mu. And so we can assume, or let's assume that these are both represented by normal distributions, and that mu is also represented by a normal distribution with mean of mu naught and a variance, which we'll call tau here. And so substituting these distributions actually gives us the posterior. And if you wanted to like sort of analytically solve this, you would see that this posterior together results in a normal distribution. And so what these actually look like can be sort of simulated in the code up on the R Markdown, which, yeah. But basically what this shows is that our prior probability of mu is shown in this red. The green is the data centered at 15, which is our likelihood. And then the blue is the posterior. So calculated from this and filling in our data equals 15. So this is another way of visualizing Bayes' theorem. And so what we can see by looking at this is that the posterior is a weighted mean between the prior and the likelihood in this instance. And so one thing, I guess a question for the room that you can answer in the chat. So what does this mean for the precision or the uncertainty in the posterior? So this means that the posterior mean is actually a weighted average of the prior data. And then the other thing the other clue I didn't give you is that the posterior precision is the sum of the data precision and prior precision. And so do you think that the precision or uncertainty in the posterior will be more precise, less precise than the prior uncertainty? Okay, so we got a couple answers. So we've got more precise, less precise. So it will be more precise. So the posterior precision is a sum of the data precision and the prior precision. So if we add up those two together, let's say the precision here, I can't remember exactly what it is, but if we add them two together, we get a higher number. And so that's more precision for the posterior. So more precision would be less uncertainty. So that can be a little bit of a confusing thing. So yeah. Okay. Cool. And then we'll quickly move on to giving you an overview of Monte Carlo methods. So we gave some simple examples of using Bayes' theorem. Yes, thanks, Jessica. So we'll give some simple examples of using, or we gave some simple examples of going through what Bayes' theorem means, but how do we actually start to implement this in more complex models where we maybe can't always write down what the posterior should look like in terms of an analytical solution. And yeah, writing down the posterior is not often something that you can actually do. And so we rely on Monte Carlo methods to approximate probability distributions. And so these are numerical methods that allow us to approximate almost any probability distribution from random samples of that distribution. Yeah, we won't get too much in the weeds here, but we'll introduce a few different ways of using Monte Carlo methods to sample posterior distributions. So we'll call them MCMC methods, which are Markov chain Monte Carlo methods. And one of the programs that we're using today, just another Gibbs sampler, is using MCMC methods. But there are several, including bugs and WinBugs, Stan, Nimble, etc.
Also want to say here that, you know, Bayes' theorem was discovered quite like in the 1800s. I don't remember exactly. Like, it's not, the Bayes' theorem is not new. It's we need a modern computational power because there's no closed form solution, right? The reason why so much of science is based on originally based on these frequentist ways is because you can do the calculus and you can have a closed form solution for what, for estimating for these parameters. It's like the slope is this and the intercept is this in regression. And so you could do it by hand, basically do it longhand, and you can't like only the simplest cases of Bayesian models can you do by hand with calculus. Otherwise you'd have to, you need these modern computational power to do it. And so if there's kind of like, there's totally rational, because it's not like a, you know, poo-pooing frequentist. It's like that's what needed to happen at the time, and then now we have the ability to do it this way.
Yeah, exactly. So like that's sort of one of the big reasons why I think Bayesian statistics has sort of taken off in the last decade or so, is the ability to actually implement these in a way that is fast. Okay, so let's move on that was a long introduction, but let's get our hands on some R code and start with a simple linear regression example. So this is where hopefully everybody is able to access the binder. So I'm going to switch over to that. And so we're going to start with a simple linear regression. I'm actually going to go back to so I'm going to go to this JAGS tutorial, R Markdown. You don't necessarily need to run this, but you're welcome to. It won't knit, but yeah. So we'll start off thinking about implementing a simple linear regression where we're trying to estimate the slope and intercept of a relationship between two variables in a really sample relationship. And so you might be familiar with things like using LM, that function, to fit a model using a more frequentist approach. And we're just going to use the CARS data set, which is loaded into R. So we'll look at what this looks like using a simple linear regression of speed and distance in the CARS data set. So we can run this very simple regression and get a plot of distance versus speed and a linear fit through this. So that's one way that you might do it. But we can also start out really small and try to implement this in JAGS. And one thing I'll say is that this is an extremely simple example, but the way that I typically build up models and that many people would recommend that you build up Bayesian models is by starting with the most simple case and then starting to add in your complexity and adding in levels of hierarchy if you need them. So we'll start out small here. So in Bayesian models, all variables are treated as random, and that means that all these variables can be estimated within our model. And so this includes our dependent variable y. And we could also include uncertainty around our independent variable x, or in our case, dependent variable distance and independent variable speed. And so why might this be useful? Y is a measurement that's taken by me, which is, I'm an imperfect human being. I can't always measure things as precisely as I would like them to. We often can't directly measure the true process. And then alternatively, we might be estimating a single process or value from two different data sources. And so that's another reason to try and account for data uncertainty. Okay, so we're going to specify a linear regression model. So you can look at it on this tutorial, or this would be a good time to pull up this JAGS regression.r script. So this will have the code that we're going through in this tutorial, but I'll give a brief overview of what the model looks like. So Bayesian models all have sort of a data model, a process model, as well as priors. And so we'll briefly talk through what those are before we jump into the code. So for here, our data model is y is coming from a normal distribution with mean mu and variance sigma squared. And then we have a process model, which is actually the linear regression part of the model, where mu is equal to our slope parameter beta times our data x plus an intercept alpha. So that should look pretty familiar. But I want to point out that the process model could really be any model that you can write out. And so here we have a data model for our data y, which is distance in this case. And then x would be speed. And so we got to specify a prior distribution or a prior probability. So there's a lot of information here. I won't go into too much detail about like how to actually select priors, but there are a ton of good resources on that. But I do want to point out that we can choose uninformative priors or informative priors, like in the case of the sun exploding example. And we typically want to specify what are called conjugate priors. And so this means that when the prior and the likelihood function are combined, they generate a posterior distribution that is named and defined, such as a normal distribution, etc. And so one example of this conjugacy is a normal likelihood and normal priors for the mean and gamma priors for the precision. You don't have to do this. It will probably help with convergence, but there are many cases in where you are unable to do this. Okay, so uninformative priors basically are saying we don't know much about what the prior distribution should be for this parameter. And we have no sort of like prior scientific knowledge besides what the shape of the distribution should be. And then informative priors would be, for example, in the sun exploding case, let's say we knew that, you know, the sun was probably going to explode within the next 100 years. We might put a stronger prior on that probability distribution. Specifying very informative priors can be helpful. So it can be useful if we've already done a study where we know the relationship between distance and speed, and we know that the value of beta should fall within a specific range. It might not appear to be super useful in this case, but in much more complex models where there's a lot of different model parameters that can trade off, specifying informative priors can help constrain other parameters in the model. So an example in my research is like, we had a couple of different uncertainty parameters that we're trading off. And one of them was the uncertainty around the measurement of trees. And so basically specifying an informative prior on that uncertainty allowed us to better get better estimates in our model and improve model convergence. Okay, so that was a long tangent about priors, but here in this model, we're going to specify uninformative priors for our parameters. And assume that the true value of our slope is sampled from a normal distribution with a mean of 0 and variance of 1,000. And so this is our prior for beta shown here. We're going to do a similar thing for our prior for the intercept. And this is typically similar to the assumption that we often make when we're fitting a linear regression. And then we're going to specify a prior for sigma squared as a inverse gamma. And so we can't use a normal prior here for sigma because the variances should be non-negative. So that was informing our choice of distribution for this prior. So we're going to use JAGS. In R, you need to have the R-JAGS package. There are some other packages that allow you to do this, including R2-JAGS. But let's run over to the JAGS regression.R script, and let's try and work through this together. Yeah, and let us know if you're having technical difficulties. So let's try running this. So this first line is just listing our data. So JAGS expects to have the data in a list format. And so we're specifying the distance in the cars data set as the X values, the Y, what we're trying to predict is speed, and the number of values that JAGS should expect is going to be the length of that speed data set. Okay, so we'll specify model code in JAGS syntax, which you might notice is somewhat similar to R code, but it's not always entirely similar. And so it wants this model in a string, like a text string. And so we'll specify for each I in 1 to the length of the speed data set. Yes, good point. So JAGS is not vectorized, and you have to use for loops within this. Yeah, so we're gonna loop over each basically row in that speed cars data set. And we specify our data model, which is the yi, so the speed of, we'll just say car I, follows a normal distribution with a mean mu and precision tau. And the mu is our process model. So you'll notice that we're actually specifying this. So we have mu I, the mean speed, or the true speed for a given car I, is equal to our estimated intercept, the estimated slope, and the data of distance for car I. And then here's where we specify those priors. You'll notice these are outside of the loop. And yeah, we have uninformative priors for all these. And then the other point that I want to point out is that for JAGS, the second argument of the normal distribution is 1 over sigma squared, or the precision tau. I think that varies based on if you're using like bugs or stand. So that's something to keep in mind. So let's run this simple linear regression. It creates this text string that's hard to read in your window, but it's nice and pretty up here. And then, so we're gonna call or initialize the JAGS model using this JAGS model function. So it wants a file, which will feed it a simple linear regression object. The data is that list of car data. You can supply initial conditions. We're not going to do it here. And then another thing that you probably want to supply is the number of chains. And so what JAGS is going to do is it's going to draw a bunch of random samples, and it can do multiple sets of that at once. So the number of chains so we're going to get 3 basically long strings of parameter estimates. So those 3 different sets of those. And typically you want to do, I feel like most people do 3 to 5 chains. And so that just initialized the model. If there are issues with the way that we specified the model, we would probably get some errors in that initialization. But we haven't actually run the model or sampled the posterior distribution. And so what we can do that using this coda samples function. So we specify the model is JAGS model, that object we just created. And then we can say what variable names we want. So let's say we want to track alpha, beta, and tau. And we'll say, we're not actually interested in sigma, we're interested in the precision. And then the number of iterations. So we'll have 3 chains that we specified above, and each of those chains is going to have 5,000 iterations. In a normal modeling approach, you would probably do more, but let's take a look at what the first 5,000 look like. And that ran really fast. And some more complex models might run a lot slower. Let's get a summary of it. So this summary is, it'll tell you the number of iterations, the number of chains, the sample size per chain, and then it will calculate a mean, standard deviation, and quantiles. And so it's a class of MCMC list. And so we can check the for what's called a convergence. So we want to make sure that the samples that we're getting aren't sort of all over the place. And one thing you can do to check that is to look at trace plots. Let's rerun that. And so trace plots look like this. They're plots of the number of iterations on the x-axis versus the value of the parameters that we're sampling. And so these all look pretty good. You'll notice at the beginning, like at iteration 0, maybe 1 or 2, you're getting values that are sort of outside of where the rest of the values are, but it converges pretty quickly. So all of these are sort of overlapping quite a bit. So that's one way to visually diagnose whether or not your model is converging. Another way is these Heilman-Rubin statistics. This is showing basically anything below 1.01 is showing that it's converging well. And so all of these look pretty good. And then you can also check out the autocorrelation in the chains. And so this is basically saying how correlated is one iteration to the previous iteration. And so you basically want what's close to independent samples, but that's often not the case. So we can look at these autocorrelation plots. And so high values here are showing high autocorrelation with the previous value. And so for a lot of these, there is actually pretty high correlation, going up to like, I don't know, 5 iterations. You're still correlated with some of the previous iterations. And so sometimes people sort of thin these chains out, so they'll only sample every 5th iterations. Sorry, I'm getting a weird message on Zoom. So they'll only sample every like 5th iteration after, but we don't need to worry too much about that. And from my understanding, that's sort of going out of style, as long as you have some parameters that look like they're converging pretty well, like those trace plots did. Okay, so let's convert this into, let's take these parameters and look at the posterior predictive distribution and the parameters with uncertainty. So we'll convert this JAGS out object to a matrix. Still in this. Okay. And then we're just getting the minimum distance and the maximum distance. And we're going to create a list where we are basically calculating the predicted Y outside of the JAGS model. You can also do this within, and that might be easier and probably more like less work. But for illustration purposes, we're doing it outside here. Okay. And so we can plot this up. I use ggplot. Okay, how are people doing? Are we going at a good pace, following along? Okay, we got one fine here. Okay, so what this plot is showing is credible intervals, or basically like samples of this relationship. Let me go back to this and see if there's anything else I wanted to talk about here. Chains converge, great. Yeah, so we're just sampling these credible intervals, and we can next simulate the credible intervals and the predictive intervals from random pairs of samples within the MCMC output. So let's go back to this, click on that. So we'll get the number of predicted values is basically just going to be the length of this from the minimum to the maximum of distance. Let's do 1,000 samples. We're going to randomly sample from the JAGS mat or the posterior distribution. And then we'll get an X pred, a Y pred, which is our predictive intervals, and a Y cred, which are our credible intervals. So this for loop will calculate the expected value of Y at each X. And then for the prediction interval, it'll add this additional random error that is from our posterior distribution of our tau parameter or our precision parameter. And then the Y credible intervals will just be the samples from the posterior distribution of alpha plus the posterior distribution of beta samples times our X values that we're giving it, which are this from 0 to 125. So we'll do that. Again, these are things that you could very easily do in the JAGS code, but just for the purposes of illustrating here, I wanted to point that out. So we'll get the quantiles of these, of the credible intervals and the predictive intervals, and put those in a data frame here. And then we'll plot the 95% credible intervals, the 95% posterior predictive intervals, using this code here. Okay, cool. So in the chat, could you say which of these confidence intervals, or I guess shaded intervals, which are the credible intervals and which are the posterior predictive intervals? So we'll call this middle part gray and the outer part purple.
Could you type that as a question in the chat,
Yeah.
Kelly? Okay.
Yeah, I'm realizing I should have change the colors here. But okay, so we've got a couple of answers. So Anthony, the purple is the credible intervals and the purple is a predictive interval. Okay, we've got two different answers here. So the credible interval, you'll notice when we're making these, is basically just the alpha parameter estimates, the beta parameter estimates times the X values that we're interested in predicting for. So this credible interval includes just the uncertainty from the parameters. And we're not even including any uncertainty in the data here. Whereas the second one includes the uncertainty from the parameters from that credible interval, but also the additional process uncertainty. And so the purple, that larger interval, is the posterior predictive interval. And oftentimes you are mostly interested in this posterior predictive interval because it's including more sources of uncertainty. Does that make sense to folks? Got a thumbs up. Okay. All right, so we have gone through and done a simple linear regression using JAGS. So you guys are all Bayesians now. Congrats. And so we can start to move on to making things a little bit more complex. I answered these questions for you already, and I don't think we'll do a breakout room. I think the group is kind of small enough. So a couple of things to think about. So I mentioned the parameter uncertainty is included in the credible intervals. So that's the uncertainty around beta and alpha. Let me make this a bit bigger for you. And then the process uncertainty, which could be sigma, or in our case, it would be precision, which is the tau. That is included in the posterior predictive intervals, so the larger intervals here. And we could also include driver or data uncertainty in here. So if we had multiple measurements of, distance, then we could include that data uncertainty. Okay.
Kelly, it's been, I guess, an hour and 20 minutes. You want to offer kind of a bio break and or let this time for people to chime in with questions, concerns? There's a lot of material for newbie, like for the noobs, this is a lot of material, like, and a lot of words, I feel like, yeah, particularly vocabulary thrown out. So if you want clarification for any of that, or just to like absorb it for a second, maybe a 5-minute break.
Yeah, I think 5-minute break would be great. So we'll start back up 11:25.
Okay, awesome.
Okay, cool. Yeah. So just a conceptual question. In the case of simple linear regression, is there any reason to prefer JAGS over the analytical approach? It is not readily apparent. I think where the benefits of Bayesian approaches start to show themselves is when you start to complexify models. So if you have sort of hierarchical structure, random effects, that's when I started to think about implementing a model in JAGS or STAN or one of the other methods or softwares to use this. But I will say that often when you're implementing a linear regression, it's not as often that people include both the parameter uncertainty and the process uncertainty when making predictions from those linear regressions. And yeah, so that's where JAGS or some other Bayesian method might be useful, is if you have things like uncertainty in your data, you can include that and propagate that through. Typical frequentist presentations of linear regressions often, I shouldn't say always, but often only include the parameter uncertainty, or only include the process uncertainty. Yeah, okay. Okay. Oh, there's another question in here. Okay, I'm coming from the perspective of this is, okay. What's the standards in terms of reporting Bayesian regression in a manuscript? Like significant versus non-significant. So it sort of depends,
right?
What?
Oh, sorry. I think that's in regards to like reporting parameters specifically.
Yeah, I think that's what I'm interpreting it as. So maybe Jessica, you have ideas about this, but usually what I am reporting is like, is the posterior predictive distribution different from zero? Does it include zero? Does it not include zero? That's sort of one thing that I often talk about. But I usually just report the median value and then the 95% confidence intervals around that.
Yeah. So one thing that you might note if it was a Bayesian paper or not is if they call it a confidence interval or a credible interval. So the Bayesians typically use credible, like it's still abbreviated CI. So who would know really? But it's a credible interval, and that central, technically it's a central 95% credible interval that you get from like the statistics output in JAGS. And then whether or not that overlaps zero, if it overlaps with zero, not significant, doesn't overlap zero, is significant. Do you have, you can chime in and unmute yourself too, if it's easier to just, talk. Like anything else about reporting Bayesian, like reporting, what about reporting, I guess I should say.
I think that's a very useful answer. Thank you. So when I was looking at the tutorial, I noticed how the credible intervals were more narrow in the portion of data where you have more data points. I guess I have read similar papers before, but I didn't realize they were doing Bayesian regression, because typically with frequentist regression, you cannot get varying like confidence intervals, right? Like it will be like
it's smooth instead of jaggedy.
Yeah. So what are we talking about? I think that's a very useful. I was just thinking if I'm going to use Bayesian regression, how should I frame the results in the results section? Like how do I talk about it? And I think that's a pretty good way just to say the credible intervals, they include 0 or not include 0. And therefore we conclude
A
the
certain covariate had a significant effect on the response.
yes.
Right.
Yes.
I do want to note though that the credible interval would be for the parameters. So like if you were doing that on, oh, what's the parameters here? Alpha and beta, like you would report the credible intervals. It's the Kelly is showing the purple. That's the predictive. That's for predicting. That's for like doing an R squared, basically. Like you can calculate a Bayesian R squared too to assess model fit. You would do predicted on your y-axis and observed on your x-axis. And you would show a plot of that. You would include this purple predictive interval as the error bars, and then you would just run a regular frequentist, or at least I do, regular frequentist LM through the points, and I can report an R squared of 0.8 or something. And that would definitely be part of the reporting, because before you interpret your model, your readers would want to know, well, how good of a model is it before I need to know kind of how much should I believe your results or agree with your interpretation.
Thank you.
Yeah. Okay, so it looks like we should all be back. So we were thinking of doing a couple different breakout rooms to make our way through either the random effects.r script or incorporating driver uncertainty into your model. And so I will give you an overview of what both of those are going to look like. So incorporating driver uncertainty, we are going to, I guess I'll start with the random effects. So we'll simulate some data, add some random effects into the model, or we will start to add uncertainty in the X variable instead of just in the Y variable. So think a little bit about which one of those you want to focus on. And I would say in these breakout rooms, we'll focus first on the respective R code. But if there's time, you guys can feel free to work ahead and work through the other one. So I think, Jessica, you're going to do random effects.
Yes, and I think I was endowed with breakout room creating powers by Austin. I'm not sure if he's still here. Maybe Austin's still here.
Yep, you should have full power.
Ooh.
Awesome.
I'm going to create 2 breakout rooms. Breakout room 1 will be Kelly and driver effects, and BR2 will be Jessica and random effects. So I'll do that, and you guys will be able to choose the room we go in. Let's say like at 11:55 to come back to the main room and debrief for the end of the seminar.
Okay, sounds great. I'll stop sharing. Okay. Hi all. So you all are currently just in the main room. If you could go click on the breakout rooms. Oh, you can't seem to join. Is everyone having the same problem? I can assign you to the breakout room of your choice. Oh, it might be because there might be sometimes if you don't have the most up-to-date Zoom. Okay, so Luke, breakout room 2. Okay, and Grace and Corbin, are you having difficulty joining?
May I ask this question?
Yeah.
Is the recording for yesterday's introduction to R out available? Because I was not in that class, I was in the Python class instead.
That's a good question. I think that let's see if there's anything available on the HackMD. I think that most people were recording the sessions. I don't know if they're already available.
And then I've also seen ggplot on the commands. Do you need to also understand how ggplot works for you to use that?
Sorry, you mean in this tutorial?
Yes, yes, yes.
So most of the examples that I gave you don't necessarily need to edit the ggplot functions, and you could very easily plot all of this up using BaseR. I just prefer ggplot. So no, you don't necessarily need to understand the ins and outs of how it works, but yeah, I would recommend the ggplot session at 1 p.m. today. So
Yeah, I'm joining it. Thank you.
Austin, do you know, there's a question about whether or not the recordings are available online yet?
Not yet. I don't know what the final decision is, whether they're going to do it day by day or just compile everything at the end and then send it out to the entire group of where it's going to be found. There's plans on taking the recordings, putting them on YouTube unlisted, and then putting all the YouTube links in the HackMD documents.
Okay.
So I guess just kind of check back on those, and we'll make sure to communicate to everyone where those recordings will be once we know.
Okay, great. Okay, so we have a couple minutes left. How was breakout room 2?
Good. I didn't realize that the random effects script followed, like, built on top of the driver or the script. So I tried to recode that on the fly to like simplify it, to take that out. And don't think I did a great job of that, but they got to see an example of debugging in real time, and I don't think it was recorded, so at least there's that.
Perfect. Yeah, we ended up kind of just going through the driver uncertainty one and then had some extra time. So we walked through the random effects, but I think more time is needed to digest. So
we're definitely like providing, you're definitely providing a lot of information, you know, that would be covered in multiple weeks in a Bayesian class or something. So
yeah, so I'm sorry if this felt like a fire hose of information. My goal is that you'll have this as a resource. Like this will be up on my GitHub. There'll probably be some changes to it down the road, but feel free to go back to it and use it as needed. There are also in this PDF, there are some additional like resources on Bayesian modeling that you can find. I don't necessarily need to walk through them, but I'll show them up here. In this PDF, I'll push it up to the GitHub repository so you can have the up-to-date version of it. But there's a lot of books, there's a lot of online resources, and different resources to implement Bayesian modeling in R. So before you guys go, make sure if you are interested in the reading group that we had talked about, please add that to your like name or introduction in the HackMD. And also any feedback that you want to give would be awesome to help improve this workshop.
And we might even do it like maybe we might just email you to reach out about the reading group. Feel free to unsubscribe or tell us to go away at that point. Yeah. But since we have your email now.
Great. Yeah, if anybody has any questions before we leave, you can feel free to stick around, but if not, have a great rest of your day and week.
So I go ahead and stop the recording.